There we go. There we go.
Thank you.
Okay. If this
For the sorry.
no, you can say your question.
For the y component, why is the initial 0?
Initial y component is 0, right? Because the question says it has an initial velocity of 5 meters per second along the x-axis. So that means it's not even moving in the y. It's just traveling in a straight line, right?
Oh, okay. Thank you.
Yeah. And if this didn't make too much sense, I think the next one will. The next one is like easier, 32. Like it's very short, doesn't have to do with vectors, so you guys should be fine. Let's see what happens. All right, so 4.32. Balls are horizontally off a roof of a building that's 9 meters tall and lands 9.5 meters from the base. Okay, so this thing is 9 meters tall. And then it lands. The language that you need to know is if it says thrown horizontally, that means the initial velocity vector is just horizontal, right? It's not thrown like this. Okay, it's just thrown horizontally. So you want to write it like that. And then it says 9.5 meters from the base. Okay. Like this is a pretty standard problem. Like, you should leave tonight knowing how to solve this. And I think most of you could do it if you had to, but I'll show you there's a way to set it up, right? So if I get something like this tomorrow, again, what am I going to do? I need to find initial speed. And I realized there's like a X and a Y direction going on here, right? This is 2-dimensional. Why do the negatives not matter? They do. In this problem, I will show you the negatives do matter. Okay. Again, if it's a 2-dimensional problem, I'm just going to write out my variables for both dimensions, right? Even if I don't know what I'm doing, I'll just write this out still. So why the negatives do matter here, right? Because when you write the diagram, you actually do need to point out where's the positive y and where's the positive x, right? So all I'm saying is when the ball's going this way, it's the positive x direction. Then when it's falling, the velocity will be negative. And you'll see those come into play in a bit. And this is, of course, the 0 point. So yeah, when you draw the diagram, you just write it, you draw it like how you think it looks like. You define where the 0 is, and then you define where it's positive and negative. Okay. And so now I'm just gonna write out what I know. I know like it says the roof of the building is 9 meters tall. So I'll write 9 meters here. Oh, yeah, sorry. It's like this is where you write -9 meters, because again it does because you say the 0 is here, right? And again, if you want to, if you want to, you could have put the positive y facing down, and then like it would have been positive 9 meters. Okay, but if I put it towards the sky, it's positive. The reason why I say it is negative because you have to think about where you start and where you finish. If I start here and I end here, I'm going from like 0 to 9 meters here. And since I say this is my 0, and I treat this like an XY again, you should be able to tell like the displacement, right? If you remember what displacement is literally like where do you start and finish. Your displacement over time was negative, right? In this plane here, okay? That's where the negatives come in. Because I said that's 0, and then if from where I started to where I end, it's a negative y displacement. So I put the -9 here. And so to contrast that, the x direction is positive this way. So I just write 9.5 there, right? And you didn't have to worry about this if you just said towards the bottom is positive, but you know, it is up to you. People like doing it like that for some reason. Okay, so we have these two. And so you want to find the initial speed, right? The initial speed, but then you want the initial speed in the x direction. Like this is what we want here. We're trying to solve for this. Then we write other things that we know. We know that since we're storing horizontally, there's no y direction, right? And then I know that there's always negative 9.8 meters per second in gravity. Again, it's negative because I said towards the sky is positive. So my acceleration due to gravity should be negative, right? Okay. So I have 3 here. That's good news. But then I can see what else I can fill out here. So a lot of people don't know still, but your acceleration, the x direction, unless the problem says so, it's always 0, right? Because if I throw something, it's not like it accelerates in the x direction. It falls to the ground because of gravity, but we don't have like a horizontal gravitational field or anything like that. So unless there's like little rockets attached to your baseball, when it leaves the thing, once you throw it, there's no constant acceleration that keeps pushing it forward. And acceleration would imply there's a force, right? Because F equals ma. In mid-air, once you throw it, it's not like there's any more constant force. You already gave it an initial force. Everything after that, it's not going to be accelerating anymore. Okay. Yeah. All right. Anyway, back to here. I want to solve for that. It's 9.5 meters. I want to find the initial speed. The only other thing that I can bridge the gap is with this time, right? Because I don't really have anything else. And since acceleration is 0, these two are like the same, but you know, I need more information. I need the time if I want to find out like the initial speed, because speed is distance over time. I need time here, right? So anyway, I look here and I think about which equation I want to use. I'll just use this. Delta y equals VIT plus 1/2 AT squared. All right, this is the one we like to use. And then, you know, we got to solve for time. So let's do that. Negative 9 meters. This goes away. And then 1/2 of 9.8. This is negative 4.9 t squared. Right? I just cancel out the 0. 1/2 times 9.8 is negative 4.9. The negatives cancel out, and then you can do your square root. So it's 9 divided by 4.9. And that gives you a time of 1.36 seconds. So it took 1.36 seconds to fall into the water once you hit there. And so now, yeah, these two are always the same given these two directions, right? And so I can say this is 1.36 seconds. So now you find out what's the initial speed. Let me think of what equation I want to use. Let's see. What if I use this? You know, we can try this equation again. Delta x equals VI t. Can I use this equation? Let's see. See, I'm trying to solve for this. I have the time, I have displacement. This goes away. See, I just kind of like try it out. You know, it's like, all right, this goes away. I have the time and delta x. Well, when you look at that, if there's no acceleration, delta x is just a speed times time, right? The kinematic equations, you only use them because of acceleration. But the moment you don't have acceleration, it's just, there's no kinematic equation. We know that velocity is speed. I mean, velocity itself is a distance over time, meters per second. You know, at this point, you can see we just rearranged it to meters equals, you know, velocity times time, right? So that's when I know it's fine because, yeah, the acceleration go away because it's not accelerating the x direction. Let me just solve for velocity here. So again, you can see it's just delta x over t, which is great, just meters per second. What's the x displacement? Positive 9.5. And then the time, 1.36 seconds. And what's this going to be? 9.5 divided by that. Like 7 meters per second, which sounds right to me. So yeah, very common problem, you can tell, right? It's very short, but you need to be able to solve something like this. And that's how we do it. Maybe a little bit, you know, long-winded, but I do recommend this setup all the time. Anyway, let me see if there's any quick questions for this. Yeah, if you have questions, just say it right now, because the chat is helping me to see. All right, if no one has any questions, I will move on to do another tougher kinematics problem. Yeah, okay. We'll do that. Why am I raising this? Did people on the practice midterm, that first word problem, that kinematics one, like did people get help with that in their discussion sections? Like, I know we covered it in the 10 and 11 a.m., but I'm not sure. And the 8 to 11, I'm not sure if the others covered it. So maybe later. But that's a good, basically, if you know how to solve that one, you bit shape too. And if someone asks, was it? If you throw a ball, what was this? Yeah, if you throw something upwards, is it, if the acceleration would it be positive? So yeah, a lot of the problems, I think there's one problem in the midterm or something, practice midterm, where, it's just like one dimensional, throw the ball up. Depends, right? If I say towards the sky is positive, then acceleration, which is due to gravity, is always negative, right? But of course, it would be positive if I decided to say towards the ground is positive y, and that means technically the initial velocity will be like negative. But basically, yeah, the acceleration is always towards the ground, and like Eric said, it just depends how you set the y value. Yeah. So, but generally, yeah, it depends where you set that y thing. Okay. Okay, let's see. Oh yeah, for number 40, we're gonna, should we skip? Ooh. We'll do 45 first. The kinematics ones are pretty long, so I think I'm not gonna do all of them because I want to get to relative velocity and forces, but that way I think you will probably get all your kinematics problems correct after that. So we'll do 45. Yeah, okay. A high diver leaves the ends of a 5-meter diving board. So we can draw something like this. So the diving board is 5 meters high and strikes the water 1.3 seconds later. And we'll say the trajectory something like this. This is, what is this, 3 meters. And this took 1.3 seconds. And okay, we need to determine what's the initial velocity, what's the max height, and the final velocity when she enters the water. So it's everything a kinematics problem wants to be. And so let's try and solve it. Might be confusing to some people, but hopefully you can see that the initial velocity vectors like that, jumps off. I remember someone told me like they dive, and that's not exactly how it works. But just for the sake of this problem, like in physics in general, like that's, we can expect the initial velocity to be like that. And even then, we're just saying there's some x and y component, right? And the reason why we know there must be a y component, because I ask you like what's the maximum height reached. It's not like off the diving board you go straight into the water. There was like some max distance, right? If they're asking you what's the max height, like there's a y component there, and of course there's an x component. So just generally, it's like just like that. Anyway. And then we just call it V naught. And so just like the last problem, I'm just gonna set it up the same way. I just do X. Write these out. And same for here. Okay, and let's see. Yeah, all right. Other parts of drawing the diagram, if you remember, it's like defining where's the 0. And so we're going to be consistent. I've always called the starting point 0, so I'm just going to do that again. And And yeah, we'll say this is positive direction. And maybe for once we'll say towards the bottom is positive y. You know, you should try that if it helps sometimes. Okay. So yeah, let's do it. What do we know? From the 0, what's the start and ending displacement in the y? If I start here and I end here, my end towards the bottom is positive. Well, then my y displacement is just positive 5, right? It's not negative like last time, because now I switched where I put the y positive. So I'm gonna put 5 here. And then they told you how long it took, so that's nice. And of course, acceleration now is positive, right? 9.8 in the y. And again, it's not negative because we set it towards the bottom is positive. Anyway, let's see. Need to find the initial velocity. The initial velocity has an x and y component, right? So if I find the initial velocity in the y and the initial velocity in the x, then I can put them together and get like that initial velocity. So that's like my goal here. I want to find both initials, then I can put it together and like get initial velocity. Anyway, how do I start getting initial velocity here? Let's see. Now we just try this thing again. Will this work? I have the delta y, trying to solve for this. You know, it's yeah, should work. All right. So I'll plug it in, 5 meters. This is just VI 1.3. It's 1/2 9.8, so it's plus 4.9. You know, is it 1.3 squared? That works out. Yeah. So let's see. I will just solve for VI here. And I'll just skip a little bit of algebra, but you get the idea. This is, by the way, this is 8.281. This is 5. If I isolate this, let's see. What's it going to be? It's like, what is this? 2.52. Anyway, I'll just write it out. 4.9, 1.3 squared. So it's 5 minus that. So 5 minus that is, this is going to be negative 3.281 meters. And then we can see this is a meters and this is seconds. So when I divide the seconds, I'm going to get a velocity. So this will be just fine. And of course, it's going to be negative because of the way we define the coordinate system. Because if down is positive, well, then the initial is negative, right? So here, negative 2.52 meters per second. This is initial velocity in the y. So that's that. And yeah, this is like 2.52. And then now the x direction, as I mentioned before, if it's not accelerating in the x, these two are going to be the same. Because if I didn't accelerate, my initial x is going to be the same as the final x. You know, these are the same. They're just Vx, that does not change. And they give me the time. And then they give me how far it is, the x displacement. You have everything. Do you really need to use a kinematic equation at this point? Can't you see that if velocity is just distance over time, I mean, that's actually what it is, you'll just get the initial x. And the initial x is the same as the final x, right? So let's see, yep. If I want to get the initial velocity in the x direction, here's what I do. I don't even need a kinematic, equation. It's just meters divided by seconds. And what is this? This is like 2.31 meters per second. This is velocity in the x. Yeah. So now we can find that thing, right? Let me write those components in. This is negative 2.52. What is that? 2.31. So if I want to get that one, all I need to do is, can you see that talking about vectors, right? Before I continue, Margaret asked, why are they equivalent again? So yeah, to repeat, in x direction, acceleration is 0, right? As Chris said, there's no acceleration, but as to why, it's because, like I said, unless the problem explicitly says so, usually when you can consider projectile motion, there is no acceleration in x unless the problem says so, right? Anyway, we'll move on. Velocity is a vector, right? And we talked about how to get the magnitude of a vector, and all we did was square, the components, right? It's just Pythagorean theorem. Same thing here. That's how you kind of use your vector knowledge. It just applies to here as well. If I want to find out what this vector is, the initial velocity vector, well, then I just, square root those two squared, right? It's just Pythagorean theorem, nothing big here. What is this? We'll see. 2.31. Whoops. 2.31 squared plus 2.52 squared. This is like 3.41. 4.42 around there. It's around there. Meters per second. And if I ask you the initial velocity, so you're not quite done yet, because velocity is always speed and the direction, right? Like an angle. So again, I need this angle here. We found what this magnitude is. Now I need to find the angle. Well, the angle is just a tangent, right? Again, I know the opposite and I know the adjacent. So I just need to use tangent is opposite over adjacent. I do the arctangent of that. So what is the angle? Let's see. The angle is arctangent 2.52, 2.31, 47.49. If I use all the whole, it's around there. So yeah, the answer to part A would be this. You're like, right? You could, if this was a word problem, you would write out in words. Was it V naught equals, yes, 3.42 meters per second. Then you would say 47.49 degrees above the horizontal. Like that's how you answer part A. You would say, okay, it's at 47.49 degrees above the horizontal, and that's like how fast it's going. So that's like a pretty, classic kinematic problem there. Now we need to find out the maximum height reached, and then the velocity that she enters the water. Okay. Let's do that. Part B, see if we can still see this. There's too much on here. I'm going to erase this word. Part B, want to find out the maximum height reached. So now we want to find out from those 2 points. If this is point A to B. I want to find out those 2 points, right? And we'll call this point C. So in this kinematic problem, what we solved here, that was from point A to C. So for point A to C, all this is true. But now you need to do like a similar setup, but not from point A to B, right? So we can do that real quick. Shouldn't be too bad. We just say, all right, now I want to do A to B because I want to find out how far it went up. And so what do I need to do? I said, I just write out things again. So this is the same. The initial y didn't change and it should be negative. And then this time at the maximum height, right? Just like other like projectile motion problems, at the max height, we always say that the final velocity is 0 in the y direction, right? Because it's not going any higher if it won't go at the very max height. It's not like it's increasing in the y direction anymore, right? Every time I want to find like what's max height, I'll say 0 meters per second in the y, and then I want to solve it from there. So this is negative 9.8 meters per second. Yeah, and I find out the maximum height reached. Yeah, I'll just we'll try What can we try here? We try this. This is that third equation, final velocity equals initial velocity squared plus 2a delta y. This time I didn't use the delta y one because I didn't know time. We'll see if I can do this. So we know that the top, the y direction is 0. It's not going up anymore. I just solve for delta y. Delta y is I move initial velocity squared to that side, divided by 2a. Yep, let's see what happens here. Minus 2.52 meters per second squared over 2. I don't know why. Oh, there we go. Sorry, that's not. The acceleration is positive because of the bottom. Yeah, the negatives, man. Anyway, yeah, this is positive because down is positive. So I did not change that. And then let's see if this final answer makes sense. Negative 2.52 squared over 2 times 9.8. Like 0.324 meters. That's negative. Did I do that right? I think so. Yep. Yeah, so it's not too much higher. And again, the answer is negative because of where we put the positive y. Okay. So that's part B. Part B. Okay. And now we got to find the final velocity that she enters the water. What's that going to look like? Let's do it. I'm going to erase part A. We know the answer to part A. Yeah, let's do that. Okay. Yeah. And part B, or the last part, C. I need to find out the final velocity. So again, back to here, like A to C, like I want to find out like what's the final velocity here. Hopefully you can tell like the final velocity is gonna look like some vector like this way, right? Because you fall there and it's just some vector this way, which has some x and some y. And then once you have those two components, you can solve it to get this, right? That's kind of like just a repeat of the first one. I'm just doing it on the last one here. Yeah. Oh yeah, the max height. So 5.324. Yeah, that's correct. You would just add it. So nice. Anyway, so back to C. The problem's already half done because we know like the x side did not change at all. So just to simplify the picture, I just magnifying glass. This is the point I'm focused on. The x part didn't change. What was that? It was 2.31. And then I want to find the final y. Of course, this should change because of gravity. You know, this is the last thing I didn't solve for, so I'll just solve for that now. And then what equation I want to use? I don't know. We didn't use this one yet. Can I use this one? Yeah, I have to. I'm trying to solve the final. I have the initial. The acceleration time is perfect. Let's see what happens here. Initial is 2.52 plus, and then that all the positives are nice because we said down was positive, so everything should be nice and positive. Then 1.3. Let's see what I get here. 2.52 plus 9.8 times 1.3. 15.526 meters per second. Right here. All right, and so you get it right now. Hopefully by now, yeah, 2.7 for it should be negative though for initial velocity. Let's go back. I'm gonna finish this up first, but yeah, hopefully you get the idea by now for like part C. If I want to find this final thing, I'm just gonna square it, square root. Hopefully now it seems like we're beating a dead horse. And so I'm not gonna write it down, save a little bit of space. So I squared these two and then I square root. What is the actual final velocity here? It's 15.43 is per second. And of course, the annoying part is they want the angle now. You just do the tangents, arctangents. Can you outline whatever you wrote in green, in black for C? Well, can you only whatever you put in green or in black? I'm not sure what that means. Oh, because it's too dark or too light. Okay. I'll do it. I'll do it. There we go. This is 2.31. This is 15.26. Final thing was 15.5.43. Now once I squared it, and then finally to get the angle, I'm just doing arctangent. Those two. What is this angle? Let's see real quick. So the angle is 81 degrees. What does that mean? 81 degrees. Yeah, okay. This theta is 81 degrees. Does that sound right? Yep, that's, yeah, it's pretty sharp angle. So at 81 degrees, that means the velocity vector, it's like this and 81 degrees. So she fell in, from here, kind of like pretty sharp, right? Because if you're 81 degrees below the horizontal, right? Or something like this. Opposite adjacent, that was below the horizontal, right? So when it kind of makes sense that it's pretty sharp. And someone asks, shouldn't VI be negative 2.52? Holy. I mean, up here, should VI, yeah, that's negative. Yes, for C, oof, what is it? Man, I'm so messy with this. Oh, up here, shouldn't this be, what is it, 2.52 acceleration? Oh, yes. Yes. And plus that, negative, and acceleration. Yes, that is correct. Let's see.
Okay, what do you want?
Huh?
What do you want?
I don't know.
No, I mean,
I'm gonna mute you guys.
what else do you want?
I don't know yet.
Oh no.
Ethan, dog, mute.
All right, guys. Was it? All right, so I spent an hour on kinematics. I think you guys go. The negatives, just keep them constant. All right. The midterms tomorrow. Just keep it in one place. All right. This is messy, but just remember the setup because I'm gonna move on to relative velocity.
Can you
Just
talk
set it
about
up like this, and you should be fine. I'm going to erase. Okay. So yeah, based on what I know, your midterm should basically be, yeah, kinematics, like maybe some simple vectors, maybe like a kinetic one like this. Relative velocity are kind of like those funky ones that, don't have a lot of math, but you just gotta think about it. And then forces. So I'm gonna skip 45 and 46 on the kinematics because, 44 and 46, these two, honestly, they're just super long. And it's just more of the same thing, and it's not worth it at this hour to go through it. I'd rather you just understand the ones that we've gone over so far. Do we always use tan to find the angle? No, don't ever just memorize it. Always just always think about it. Yeah, hopefully it comes up in another example. Let me think. It's not always tangent. And in that case, yeah. Don't memorize it, just I would say just always look at the side. I don't like memorizing things. Just make sure you see, do I have the opposite? Do I have the adjacent? Or I'm gonna use tangent, right? Because because we didn't know the hypotenuse per se. But yeah. Okay. I would have to move on. Anyway. 61 on the Google Doc. This is relative velocity. It's a very short problem, actually. It's very concept based. So hopefully I can teach this. Okay. The child is 45 meters away. So let's see. And the child is 45 meters away from the bank of the river. So river's there. This is like 45 meters. And then let's see, as the child passes the lifeguard, so the lifeguard is like here. That's your lifeguard. It's only like as, and everything's moving down, by the way. It's only like as the child was like here maybe, but and it was only until, you know, the child crosses his line of sight that he started swimming. Anyway, that's what that part meant. And then it says, if the lifeguard can swim at a speed of 2 meters per second relative to the water, how long does it take to reach the child? Okay. And so the water is moving down like this. We'll just say the water is 1 meter per second this way. How far downstream does the lifeguard intercept the child? So you can imagine that as time goes on, the child's going to float down somewhere here, right? The child's going to float somewhere down here. And the lifeguard, he is swimming in a straight line, okay? The lifeguard swims in a straight line. So if there was no current, he would be swimming in a straight line and nothing would happen. But there is a current. So at every single point he's swimming, it turns out like this, right? Okay. So again, if there's no current, you know, everything is fine. He'd go up here. But now because there's a current, his trajectory changes to look something like this. And so his overall journey looks like this. Like he's going to intercept the child, or catch the child somewhere here. This is like 45 meters, that doesn't change. And we want to find out like, what's that distance, right? So this is like understanding the problem, right? 45 meters away, the water's going down 1 meter per second, you know, this is what his path looks like, because again, because of the current, his path looks like this, you know, looks like that, because the water's bringing him down, and the child is going to catch the child there. And so you have to ask yourself, okay, what is it? How long does it take, and how far downstream? Okay. All right, let's see. All right, 45 meters. Oh yeah, I forgot. This guy's swimming at 2 meters per second. I'm gonna write down the answer, and you guys are gonna, what is it? Think I'm crazy. But here, the answer is actually, and I'll explain it. See, just like that, because relative velocity is all in your head. The time it takes to answer like the first part, it's just 22.5 seconds. Like that's it. Can you believe it? Like, why is it like that? And that's because like when you study physics, you have to separate your x and the y's, right? Just because I have a y, does that mean I'm traveling slower in the x? You know, let's say the current didn't exist. Let's say the current didn't exist at all. This is your lifeguard. The child's here. This is 45 meters. And then moving here at 2 meters per second. Just straight up, if there's no current, how long is it going to take for the lifeguard to catch up? Wouldn't you just do 45 meters divided by 2? Right? You just do that because there's no current. But in this case, why do I do the same thing? Does that even make sense? Okay, yeah. Does that even make sense, right? Why am I doing like the same thing over there? That's because just because I have a y component, that doesn't change how fast I can travel on the x, right? So I guess a funky way of saying this was no current. And then even with the current, the same thing, right? Basically, if the x is at 2 meters per second, you know, it doesn't matter if in the y it's like negative 1 meter per second, right? Just because the current's pushing me down, I'm still traveling horizontally, like at the same speed. Man, these comments, whoa. Anyway, yeah. Do people want me to explain that again, or are most people satisfied with y is just 45/2? Is anyone still not satisfied with that? One more time. Okay. So yeah, imagine there's no currents. All right, we'll do it again one more time. All right. This is a calm river. There's nothing going on. And so there's no 1 meter per second. It's just, if I want to catch up, I'll do 45 divided by 2. And right now there is a current, but this is in the y direction. And so it's just about asking yourself, does the y direction affect the x direction like at all? Does it affect it like at all? It doesn't, right? And this is a little bit of like matter of fact, I'm telling you that it doesn't. But it's also a bit of just understanding that just because the river is pushing everyone down at 1 meter per second, it doesn't mean I'm not gonna travel this far like at the same pace. Ugh. Yeah. Man, is there any other way I can say this? Let's see. No. Yeah, it's 45 meters this way, going 2 meters that way. Yeah, you just wouldn't change that. Let's see. So it's a separation between the X and Y component. In this case, they're considered independent, so you can just calculate the X direction. Yeah, this is just X direction. And thank you, Joe. I hope I'm doing mediocre at least. Yeah, I would just think separate it as like an X and Y. It's kind of like in kinematics, we always separate the X and the Y, that kind of thing. Maybe we can, if you're super confused later, but we need to move on. Okay. The second one should be pretty easy, right? Because let's see, this was the total amount of time it took. So if I want to find out how far this is, well, that should just be 22.5 seconds times 1 meter per second. And this will give me 22.5 meters. And again, like, why did I do this? Because, all right, over 22.5 seconds, he traveled this far, right? So he would displace this much in 22.5 seconds. But then the speed, because the child is just sitting there, is not doing anything, he went down at 1 meter per second. So basically, velocity is the speed over time. In this case, we wanted the displacement. And he was moving at 1 meters per second, the child, and he did so at 22.5. Yeah, my S's look like 5s anyway. Relative velocity, that's that for now. It's just all in your heads. All right, if you got something similar like this, hopefully it would work out. It's just about thinking about it. All right, next one. Let's see. Oh yeah, this airplane thingy. Okay. 64 on this Google Doc here. Airplane is heading due south at this speed, and the wind begins blowing. Calculate velocity, blah blah blah. We'll just start off with the with the compass thingy, right? I think sometimes it helps, like if they start talking about these directions, like I like doing this, not necessary. And so it says heading south at 580. And then if a wind begins blowing from the southwest at a speed of 90, then we have to calculate this stuff. So the thing that confused me earlier when I was looking at this is because it says if the wind blows like from the southwest, and real quick, 22.5, yeah, that was it for both of those in the previous question. But if it's just blowing from the southwest, it doesn't mean the wind is going that way, southwest. It means the wind's going that way, but it's blowing like from the southwest. So that's a small thing. Hopefully most of you wouldn't have a problem with that. 90 kilometers. And what's this angle? This angle is 45 degrees, right? It's not given to you, but they just say it's like southwest or something, or southeast. It's just 45, right? Unless it's stated otherwise. Now let's figure out what is the velocity. Okay. You see we have two vectors again. This is like, it builds on the vectors. We have two vectors now, and basically we got to add them. It's basically the first question we did is just, now we got words on them. So what is the first vector here? Let's say vector of the wind. Like what, okay, vector of the wind, I need an X and a Y component, right? What's the X component, right? And this is where we're gonna finally use the other trig signs. If I want to find the X component, right, I need to do cosine. And just for people who don't know why, cosine we know is adjacent over hypotenuse. So I'll do this cosine theta equals the adjacent, which is this X side over a value I know, right? And I want to solve, like, I need an expression for the x side. So I isolate x, 90, I just multiplied over. So it's 90 cosine and then 45. And so usually I will just skip to saying, oh, the x side is just 90 cosine 45. But then for people who aren't familiar, it's just, all I did was cosine 45. And cosine 45, I literally say, what's the adjacent? Then the hypotenuse, then I isolate what I'm trying to solve for. So yeah, I usually will just skip to that, but some people don't know. So that's fine. Same for here, I just skip to 90 sine, it opposite the hypotenuse. So yeah, I'm just adding vectors, right? The first vector, what is it? The wind vector. Now I can say, okay, it's 90 cosine 45, and then I hat, right? And then plus 90 sine 45, j hat. And again, I want to write the second one right below it. There's no I hat, right? How do I know it's 45 degrees? Assume unless stated otherwise. Yep. It's kind of like if someone says I'm going, oh my gosh, no, northeast. I just assume it's 45, right? I'm not gonna, unless stated otherwise. But yeah. Back here, the plane is just going directly south. So of course there's no x direction, right? So I would say 0 I hat. And then here, right? Okay. Important, right? Because even here we should define like where's the positive, where's the negative, right? We'll just say this is all positive, this is negative. Don't think too much about it right now. Let's just do that. And so in this case, hopefully it just kind of makes sense. All right, towards the ground is negative 580, right? I mean, it wouldn't make sense if everything was positive, right? And I'm always just adding vectors. This is positive, this negative 580, right? And then j hat. So when they ask me like, what is the velocity? These two are velocity vectors. So if I need to like get the final velocity, I just add them together. And just like good old times, 90, I can just write this, right? Just 90 cosine 45 plus 0, but that's just 90 cosine 45. And that's just a number. It's just 63.64. I just literally put that in my calculator. This kilometers per hour. I hat. And then what is this? Minus. Now it's 580 minus that. Well, negative 580 plus that. So negative 580 plus 90 sine 45. This is negative 516.36, and that's j hat. Nice. This is, yeah, the final velocity. They want magnitude and direction, right? So where did the 0 come from for V2? Again, for vectors, this is like vectors always have an x and a y component. And so over here, just remember the plane is moving south at 580 kilometers per hour, right? So it only has a y component, all right? There's no x component, else it would be tilted or something. So I put 0. And of course, it said 90 going from the southwest. It definitely has an x and a y component. So yeah, that is 0. And so if I want to find the magnitude, again, it's just, Pythagorean theorem, or, whatever you want to call it, it's just square them. All right, let's do it. Turns out this is, what is this? 520. 520, what is this? 0.27 kilometers per hour. So this is the magnitude of the vector. And so now we have to ask yourself, okay, what's the direction, right? Okay, what's the direction? So again, like I mentioned before, this is just an x and that's just the y component, right? It has a direction. What's it going to look like? Well, it has a positive y and a negative positive x and negative y. So the vector just looks, the resultant vector looks something like this, right? It was already going down, and then the wind, you know, made it go to the right and made it go up a little bit, but not enough. So something like that. And again, it's consistent of this because it's on the positive side of the x, but negative y. But we'll make it a little bit clearer. We just draw it here. So this is 63.64. It's negative 516.36. Just square them. Oh, sorry. Just get the tangents. And we can get this angle, arc tangents. Hopefully by now you know why I'm doing this. And this is negative 82 degrees. Yeah, okay. The 10. Adjacent. And now this angle, this is negative 82.97. Okay, what is this? All right. Yeah. That angle is this. Yes. Okay. Negative 82. What does that mean? Yeah. Okay. Okay. Anyway, that is the angle. Let me just say it's this, and then 82 degrees. Yeah. Oh yeah. I don't know why I got tripped up. Yeah. Yeah. That angle is just 82 degrees. Yeah. That's it. That's just the answer to the question. We have the magnitude, and then you can say, 82.97 degrees below the x-axis. And that's 64. Yeah. What is this? I thought the 516 over 63 since direction relative to the ground. If we use the right equation, what is 520? Okay. Where do I begin? Let's see. All right. Just as a recap, the problem started with just the plane going down. Then we had the wind here. So I just wrote out the vectors for both of them, right? The wind had an x and a y component. So I just split up the wind. Wind was going there at 90. I just split it up into x and y. And then I just wrote the vector for 2. So I got negative 580. I just found the magnitude of the vector. And then if you find the magnitude of the vector, you'll find it's 520. 520 is literally like, if I add these two vectors, how long is that vector? Like, what is it actually? Like, it's literally moving this fast. Like before, it was just going 580 kilometers per hour south. But now after you do the magnitude, you find that, okay, now it's going 520. So a little bit slower, but it's not very useful because you need to know the direction, right? And now we can say the new speed is 520.27 kilometers per hour, but it's 82 degrees below the x-axis, right? And so when they told us the speed of the airplane, it said it's 580 south. But then when I give them a new speed, I'm telling them now the new speed is 520, but at this angle, right? So, yeah. Yeah, and someone says, I thought can magnitudes be negative? Let's see. Never, right? Because you're always squaring it. You're always squaring it under the square. So it's impossible for it to be negative. And that wouldn't make sense for it to be negative because usually if your answer is negative, it's just to indicate direction. So like if in a problem you find the answer to be like negative 5 meters per second, that is in relation to your coordinate system, right? Because like, in the kinematics problem, you always put where's positive and where's like negative. So if you got a negative answer, all it was telling you is just in the negative in relation to your coordinate axis. But when we're solving for magnitudes, it's not a negative answer, right? It's just literally how long that value is. And then whether it's on the negative side or not depends on the angle, right? So it's just a long-winded way of just saying, no, magnitudes, same as absolute value. So yeah, there you go. Yeah, let's move on. Still, it's already 10:20. You want to get to forces? We'll move on. So I just go to forces, or what do I do? Okay. We'll just fine. We'll try and do. We'll try and do 70. Okay, let's do that. So the last relative velocity one after that, hopefully relative velocity makes a little bit more sense. All right, boat in still water. We have to cross this wide river and arrive at this point upstream. The diagram's given to you. All right, we'll just see what this looks like. Something like this. All right, this is 280. Okay. Still water must cross 0.1 meters upstream. Okay. I'm just for drawing the diagram. Must cross to the right point. Okay, so basically the guy he wants, yeah, all right. Yeah, for some arbitrary reason, he wants to be 120 meters away from like directly across the bank. Like this is his intended destination. Like that's just what he wants, right? But the river is going this way, and by now you can tell relative velocity. They like using rivers for some reason, because it's just nice, I guess. But yeah, this the river, yeah, the current is going that way, and so we want to find out like, well, what's this current? So you can see, right, like you know, if that is his destination, then how would he have to angle his boat to get there? Well, it's telling you that he must angle it at like 45 degrees in order to get here, right? His intended destination is up there, but the current's pushing that way, so he must compensate for that. So he's going even further there. In that angle, they're telling you he has to angle at 45 degrees. What's the speed of the current? Okay. All right. To start, I'm gonna just label all the points. I'm gonna say where he starts. I'll just call it A. I call that point B. Call this C. Call that D. And we'll just write out other things that we know. A to B. This is 280. You can tell this is 45 degrees, right? It's 45-degree right angle triangle. If A to B is 280, well, B to D should also be 280, right? That's just right triangles. Anyway. Okay. And then C to D. Okay. Yep. And then they told you like from B to C is 120. So C to D, this should be 160. And yeah, right here. C to D, this is 160. What else do I need? Oh yeah. It's 17 arbitrary. I'm just writing stuff out, but we'll get somewhere soon. And we'll find out like, okay, what's the actual distance that he ends up traveling, right? I think usually it helps in these problems, you want to find out what's the actual distance they traveled. So before, without the current would just be this, but now with the current, this is the actual distance they traveled. And so what is that distance? A to D, A to D. Well, this is just the square root of 280 and 280, right? To both sides. And let's figure out what this is real quick. This is 395.98. for the actual distance he traveled is that. And so we're gonna find out what's the speed of the current. All right, so okay, good thing you guys answered that. 45, 90, 90. Yeah, we'll move. I can move on for that. Speed of the river's current. You know, speed is distance over time, and so it would help to know a time of some sort, right? Like, you know what I'm saying? Like, river's current is a meters per second thing, and I don't even have time anywhere. So how to, let's get some time in here. And then the boat is telling you that the boat's going at 2.7 meters per second, right? So this is the boat. He angled it like that, and this is 2.7 meters per second, right? That's how fast it's going. And so here's the thing, right? We just found the actual distance he's traveled is that it's just that straight line. It's just a straight line at the end of the day. And then he's going at 2.7 meters per second along this straight line. So if I just take that divided by that, I can get how long this all took. And hopefully this helps me solve the problem, right? So let's see, time taken. Time taken is distance traveled by boats. And this is over speed, velocity of the boat, so speed of boat. So we're going to throw this in here, 395.98 over 2.7. So what is this going to be? We're at 146.66 seconds. So that's how long it took. So now we need to find out the current of the, current of the water. And so the reason why I did this was, if I want to find out, I have how long, okay, I have the amount of time this whole thing took. And if I think about it, if I find out like how much the water moved the guy, right? If I find out how much the water moved the guy divided by the time that this all took, I can get technically the speed to river, right? If I view the river as a bunch of like little circles of water molecules, whatever, just as an explanation, and my boat's on top of it. If I calculate the distance that these water molecules like kind of traveled this guy and divide it by the total time, I can get the speed of those water molecules, right? Or like how fast the river is moving. So basically, what does that mean, right? If the way we need to think about it is, he would have ended up here if there was no river current, but because there's a river current, now he's, he has to angle it over there, right? He wanted to go here, but now he has to angle it here, right? Okay, I'll say one more time. Before the current, if there was no current, he would just end up here. But because there's a current, now he's over here. So you can say that this 160 meters is due to the water, right? It's because of the water that 160 meters exists, right? It's the only reason why, that's his kind of projected path. I should have said this is like his projected path, but he wants to end up there. So it's a long way of explaining that the current of the water it's the amount of water that, the amount of distance that the water caused, because it's the water's fault that there's 160 meters over the total time, right? So we can say the river's current is like about 1.09 meters per second. Yeah. So far, these three relative velocity ones they seem pretty separate in their own right, and that it's hard to find the similarities. I think for like this problem, it's important to recognize because before, like in the first one, they told you how fast the water is moving. So that was just really like your separation of X and Y. But here we were trying to find how fast the water is moving. We just need to find out, okay, because even the water's speed is just a distance over time. What's the distance that the water made? And then how long did this take place over? That's really all we did. So you can tell the relative velocity ones are not a lot of work. And the work you show is often not very detailed. It's just, thinking about it. So I can't predict what you're going to get tomorrow. All I hope is you can somehow get an answer, educated guess of some sort. But yeah, it's 10:30 and I should get through forces. And after that, I think you guys can sleep. Because after we cover forces, like that's pretty much it. Your midterm is just all that forces and we're good. Okay, what was it? Forces. Man. All right. There we go. Okay. Let's start with 86. I think that's the first one on there. Y is C to D, the current water distance. That's how much the current pushes the boat. The difference in where he wanted to be. He actually ended up. Yeah. Okay. We can clarify it later, hopefully. But we gotta try. Let's try 86. It's this funky looking forces problem. Let's try it. Okay, mass A here. Mass B up here. And then some force pushing all this up. Of course, connected by a string. All right, so it's 59 degrees. This is 32. Okay, there's no friction. So we need to find out what force will be required to pull these masses up at constant velocity. Okay. Yeah. What pretty classic question, like how much does this need to be in order to get this moving, right? It's a good question. Let's find out what that force actually is. And so, you know, this is a forces problem. We're kind of jumping into the deep end here, but we are going to start by always drawing the forces, right? So I know that this MAG, this is the weight of the first block. I drew it pretty long, but the length of these things doesn't matter. I just trying to do it so you guys can see. And the important thing is every time you see like an inclined plane of some sort, that you should represent, you know, the X and Y components of it. I think it'll make a little bit more sense once I draw it out. All right. Now, some of you already are more familiar with forces. Some of you already know that this angle, these two are equal because of like similar triangles. And I don't really have time to prove that. This is just kind of one of those things that you kind of just know. There's similar triangles. So this 59 degrees, if I do this, is 59 degrees. But like, why do we kind of split it up like this? That's because we always need to account for the normal force, right? So what's the normal force? It's always perpendicular to the surface, right? This is my surface. That's the normal force, right? If I decided not to split up the weight, you know, I just had that, I wouldn't know what the normal force is, right? For things like regular things sitting on a table, normal force is just equal to the weight. But clearly on an inclined plane, that's not the case. I can't just say N equals mg anymore. It's different now. But now I can say N is equal to ma cosine 59. Like that will work now. So that's how you set up the inclined plane force diagram. And of course, we got to do the same here. Just mbg, it's just weight, mg. Then I extend these things. That's why I say this is 32. And I say this is mbg sine 32, because opposite hypotenuse, cosine 32. And of course, the normal force. One last thing before we can start solving the problem. This tension thing, right? If I look at mass A, if I'm trying to figure out what's the force to pull it up, well, then this tension force should be this way, right? The tension is what pulls it up the incline. So I draw it that direction. Yep. And then same for here with it. Oh, yeah. Yeah. And then if I focus here, this is kind of tricky for some people. But yeah, on the A, I think it makes sense why the tension is up the incline. But for this B block, why is tension like going below the incline? You know, it's because I use this example where if I'm like pulling a sled, the only reason why it moves this way in the first place is because I'm pulling it this way. So the force that I exert on this sled, that the sled's force vector is going to point this way because I pull it here. So then it goes this way, right? Where I want it to. But then the reason why it's difficult for me to pull the sled is because I must be experiencing a force that way too, right? I'm pulling it this way, but I'm feeling a force pointing that way. That's why it's difficult, right? This is Newton's third law, equal and opposite reaction stuff, right? But that's why if up here, that's the case. And it still moves up because F obviously must be equal to or larger than the tension. But yeah, I mean, I hope you can notice that. Let's say if I drew the tension like this, let's say for block B, would it really make sense if I drew the tension like that? I mean, not really, right? That's just like you're telling me the string is assisting the force, you know, to pull it up there. Like that doesn't make sense, right? So that's why. Anyway. Yeah, so now we gotta find out what does this force need to be in order for like all this stuff to move? How do we figure this out? We can say, okay. You have to, in this case, if we draw a free body diagram, do you need to mention, you can just use mg, that's all you need to do, but when you do solve the problem, you do, you know, you are gonna need these, like I'm gonna use this like right now, so I just write it here. You have to ask yourself, like on an inclined plane, you know, if I have a box here, why does it move down? It's because of gravity, right? But the x component of the gravity, see? Regular ball drops because of just mg, but when I put it on a plane, it falls down because of the x component of gravity. Now gravity has like two components, right? You have the component that actually slides it down the plane, and then you know the y component that cancels out with the normal force. So that's just a quick aside on inclined planes in general. It's the same case here. What are the things that are making the system fall down? It's all the x components of the weights, right? It's MAG sine 59. This x component of the weight is what is pushing this MA down. Same to MB. The only reason why it's gonna fall down is because of the weight, right? Because of gravity, right? It's pushing everything down. But just the x components. And so when they ask you, like, what is the F needed to pull it up? It has to be, why is it not mg cosine 59? Like down here? Before I move on. Why is it not mg cosine? Because this is why you don't the other one? This one? It's sine, all right? That's why we say we never y of MA. What this is okay. I'm just explaining it again, but it's just that's why we don't memorize the tangent or cosines and whatnot, because it's just a fact that okay, again, maybe I went over it too fast, but the x component, if I want this component, this is the unknown. And so how do I get this unknown? I say, what do I know? I know the hypotenuse, and I want to find the unknown, right? So I say I need opposite and the hypotenuse. So I tell myself sine theta. So it's like the opposite, which is the unknown, over what I do know. And then now I isolate the unknown, right? Oh, somewhere. Oh yeah, there. Anyway, yeah, that's that. Yeah, we'll move on from that. Okay. So basically, I need this force to be equal to the x component of the weights, right? Equal or greater, then it would move. If it's equal, it would still move up, just in the slightest, right? So I need this to equal. I'll say that force, it has to equal the x component of the weights. So MAG sine 59. X component of this plus MBG sine 32. Right? The only way this is gonna move up is if this force can overcome those two x weights. And someone asks why the top angle is also 59 and 32, like the ones given. This is two triangles. Usually the inclined plane is just one triangle. If there's 32 or something, then like, then that's what's 32. But you have two different triangles. The bottom one's 59, the top one's 32. I think I would just solve this first before I go back. But anyway, and let's just plug stuff in. Getting here was the more important part. If you can recognize that this force had to be equal to the x components, then you're good. All the other information is given, right? The mass is, what is this, 9.5. Just writing things out. Sine 59 plus 11.5. And your calculator is about 140 newtons. This part A, right? All we had to realize was that the F had to equal the x components of the weights. And of course, the y components wouldn't matter because they all cancel out, right, with each other. They have to be. Anyway, part B is the force is now removed. What is the magnitude and direction of the acceleration of two blocks? Okay, now it gets a little bit more tricky. It's like, okay, now we're not pulling it up anymore. Was it, can we describe what it is now for both blocks, without the force? What is the magnitude and direction of the accelerations? Okay, so now what we need to do is we're going to do something that we call summing the forces. It's like, if you understand how to do this, another way to, we have to solve a force problem. I need to like figure out how did the forces interact with each other? So here's the notation, right? Let's say I'm just focusing on block A. I say sum of the forces on A. And then I should define a positive direction. So say this is positive, this is positive. So I'm gonna write it out and then maybe it'll make a little bit more sense. Yeah, sum of the forces in the A. If down is positive, I'll say it's the weights force. Subtract the tension, right? Because this is going down, tension is going this way. Minus tension equals MA, right? MAA. And this one here, yeah, just the G is positive because, yeah. Let's not worry about this too much. But up here, right? The MAA. So I'm not sure how many of you are familiar with this, but it's like, this is how we solve the force problems, right? I need to find out the acceleration. It's basically whatever the forces are, like the weight minus the tension. We always say all that it must be equal to some net force. We just say MA. We just relate the force. Like MA is sign that minus tension. It has to equal to MA. And then basically, if you can solve for the acceleration, well, then you're good, right? Anyway, you know the mass, you know G, but you don't know tension. So naturally, we try and solve this other thing, see if we can get more information. So now B, it's the same thing, right? It's tension down. Then I add the x component of the weight. And then all this is equal to MBA, right? So I have two equations that sum the forces. Then I set it equal to MA. Why is tension not relevant in part A? I did part A based off the free body diagram. So no, tension is here. I would just solve it. Maybe answer those questions. But yeah, for the rest of you, and I'll try and clarify later. If you understand how I got here, and the mg's minus the tension equals that, and then now is the tension plus that minus, what is it? Whoops, did I forget something? No. Yeah, the tension and that equals MA because the force is gone. So it's just the tension and the weight here. You should be able to see that even though I don't know tension, I know everything else pretty much. I have two unknowns, right? I don't know the tension and I don't know the accelerations. I can cancel out the tensions, right? By just adding these equations or substitution, whatever you want to do, right? And depending on your math background, this looks fine or completely foreign. But basically, if this is a negative t and that's a positive t, if I can just add these equations like this and the t's will go away, right? So now I can get, what is this? I can get another equation, ma g sine 59, and then the tension went away. Now I add this, right? So it's clear. This is gone. This is gone. MA sine 59. Now I add this. Now it's just this plus that, right? There we go. Can you solve for A? I'm going to erase this just a bit. Yep. So I can solve for A here. All this stuff is to know, and I just need to isolate A. So I can factor out the A here. I can say A and B, all this stuff. I factor out the A, now I can divide everything, right? So I can say A equals MAG sine 59 plus MBG sine 32, all over the masses, right? It would take a while to write everything in, but mass A is 9.5. So you plug that in, plug 9.8 for G, you plug in the masses, and you can get a number. A is 6.64. So that's part B. I'll quickly do, I'm gonna quickly do part C, and then we'll try and troubleshoot people's questions. Part C. In the absence of F, what's the, so yeah, now we're just finding what's the tension in the string. Okay, you just find tension in the string. You have acceleration now, so just think about your first equation. You knew all this stuff. You didn't know tension, you didn't know acceleration. But if you just solve for acceleration, you can just use this equation again and solve for tension. Okay, so I'm just use that again. Same equation as this first one, right? Now I just solve for tension. I move this over, I subtract MA, right? So it's MAG sine 59 minus MA acceleration equals tension, right? Just move tension over, move the acceleration term. Let me plug stuff in for you. Just plug in all the stuff, the masses, the G, acceleration. You'll get 16.68 newtons, 16.7 around there. See what people think about that. Do most people have their answer questions? I guess if you have a question, can just ask it again right now. I hope that was helpful. Can you explain again why we don't use the cosine parts of the graph? Oh, okay. Yeah, in this, we didn't use the cosines at all. Okay, because the question simply didn't require us to. All right, let's see. Because they said friction is absent, right? You learned somewhere that friction is the mu times n. And some of you know what this is, some of you don't. Mu is some Greek constant that sometimes in the friction problem they'll give it to you. But then sometimes you need to use the normal force to like find friction. If I wanted to find the normal force, you know, I can just say it's N equals MAG cosine, right? I can do the sum forces, right? I can say like sum forces in the Y for block A. I can say it's normal force minus MAG cosine 59. And then here's the fun part. Hard to see. But I just did N minus the Y component. And then the MAA, this one, they don't need to tell you, but it's not accelerating in the Y direction. So you can always just call that to 0. And basically, it's just a long-winded way of saying N equals that. So there will be sometimes you need to. And if it does pop up, now you are a little bit more familiar, right? Because the thing is, if you split it all up like this, and for some reason you do need the normal force, well, now you know, like, okay, I'm just gonna sum it in the Y and get my normal force, right? It's already there for you. Let's see what else. Yeah, so the force that pulls the masses up the incline would just be equal. Yeah, we set them equal, right? Because it says A is, what is the required force to pull the masses at a constant velocity, right? If I have a force, which is equals ma, that means I have an acceleration. And if something's accelerating, its velocity is changing, right? It's not constant velocity. So when you ask me like what's constant velocity, I know the forces have to be just equal. If they're just equal, then yes, it's going to move up, but it's not going to speed up. It's not accelerating. Yeah, some of you guys might be getting slightly different values, maybe because, I don't know, maybe because I'm rushing or something, but hopefully you get your concepts down. Negative T for FA, positive T in the equation for part B. Okay, I think someone was asking like, why the tensions? So I'm going to go over, the tensions real quick. Right, just focus on part A. We know like the tensions always act in a pulling way. So for MA, if I was pulling it up the incline, it would make sense that tension is up here. Yeah, that tension will be up the incline for A. And then, but as we said, down the incline was positive. So that's why we end up doing the weight minus the tension equals that, right? So if you understand that the weight's down and the tension's up there, then you're good for part A. And for part B, you need to understand that the tension, it has to be pulling down, even though everything is moving up. Your tension here, just because it's connected to something here, this thing is still technically pulling it down wherever this goes. It's something, you do need to kind of really think about it. But if everything is moving up here, this mass is pulling that down. That's why I drew that tension down, right? And again, it wouldn't really make sense if both tensions were up, because they would imply like somehow this string is pushing this mass up here. Yeah, you can also make X positive up there, and then down here would be negative, but the only reason why we didn't do that, because actually I don't know why we didn't do that. Yeah, it wouldn't change anything, but yeah. Okay, I will have to move on, unfortunately. So maybe we'll just do one last one, then we'll call it. Yeah, we'll just do one more. This is pretty comprehensive already. I'm going to erase it. Han, you can ask it now while I erase this. Or after, it's up to you. All right, let's do one last one. And by then, it's late enough. Midterms tomorrow. What you know is what you're going to know. Just real quick, when we do problems, we're given masses, chords, and pulleys. You will not be given chords and pulleys and mass. That's a pretty complicated physics thing. You can count on never being that. He never talked about it. Your TAs never talked about it. You will never be given strings or pulleys with mass. That would really make things difficult. But yeah, you don't have to worry about that. You can just treat them all as these magical strings that equally transfer the tensions and whatnot. Between 67 and 46, I am pretty torn on this. I think I'm gonna do, all right. I'm gonna do 46 because this one's very conceptual based. If you had like a multiple choice forces, so it'll probably be this. It's just not a lot of numbers. It's a great concept, and that's the last one. Will the practice exam cover most of what we need? I would say mostly. Yeah, if I think if you can do that whole thing without like, and you understand, why you do it, you're not just copying stuff down. I think you should be mostly okay. I think today was just like catching people up, reinforcing some concepts. Yeah. And let's do 46 and then we'll be done. 3 blocks on this horizontal surface. We need to draw. Oh yeah, this one could be a pain in the butt, but I could totally see this being on the midterm. We have 3 on the table. We need to draw a free body diagram for each one and determine the acceleration. Yeah. I don't want to do it, but we'll do it. Yeah. This is not the most fun thing, but a lot of thinking. Okay. All right. Let's not get intimidated. We'll just do part A. We're going to draw free body diagrams for all of them. Free body diagram is slightly different than, the big drawings that we usually do. And sometimes they show free body diagram. They just want like simply like, part A, like I don't want to like, so you can like draw it separately. You'll see. So we can imagine that there's normal force that the A experiences. And then there's a MAG. And then we have a force here. And then here. Oh yeah, this is a good one. Else you guys would not know. All right, we need to understand this. We do. All right, normal force, gravity, I think those are fine. The force is pushing that way. So yeah, I just drew it here. So it's still going to the right. But then what is this thing FB on A? Like what does that mean? And why do I even draw it in? I guess the example I like to use is if I'm pushing a wall and I'm A and the wall is B, the force that I exert on the wall is A on B, right? I'm A. So I call my force vector A on B, right? And so the other wall feels something, but why do my hands not go through the wall, right? It's kind of like why normal force exists. The only reason why you don't fall through the floor is because someone thought there must be a normal force that's up, equal and opposite. That's the only reason why I'm not falling through the floor right now. It's because there's the opposite force. So likewise, when I push the wall, it feels difficult too because I'm experiencing a force. And again, you may not feel like it, but when you do push on a wall, it's difficult because you are experiencing that opposite force. And that force, like Newton's third law, is equal and opposite. Opposite. But now it's the force that, the wall puts on you. So we say it's B on A. Right? This is like something that you definitely need to know just in general, for sure. Okay, so likewise up there, if the force pushes the boxes off from the left, this A thing is gonna push the B and C, right? Because it's gonna push there. But the thing is, yeah, the A thing, the force is gonna experience the force that the B pushes back, just like here, right? It's literally the same thing, right? So now there's FB on A. Hopefully you guys can see that. I literally did the same thing, but now you can see this FB on A is the same as this thing. MA is being pushed into MB, and so MB, of course, pushes back. That's just, that's our world, and that's our life. Now we'll do MB now. Normal force on B, and BG. Well, now, what do we have here? What do we have here, right? This whole system's gonna move to the right, But why is it? Why is this like MB gonna move here? It's because it's experiencing a force from A, right? A is pushing it. So we say FA on B. In this case, MB is the wall, it's the thing that's being pushed. So that's why I say it's FA on B, A on B. That's why it's gonna go there. But now it's crashing into MC, so it's gonna feel something back. I'm sorry, not MC yet. That's right, it is MC. Now it's being pushed into MC. Now MC has to give a reactionary force. So we say FC on B. Hopefully you're getting the hang of this now. Last one. And yeah, you do get points for this. Like they usually do give points for these kind of things. So it's important to get these right. This is NC, and now down here is MCG. Okay, but now it's MB pushing onto C. We say FB on C, but C is not crashing into anything, so we just leave it there. Those are all your free body diagrams, right? So now we move on. Part B, we have to determine what's the acceleration of the system. So what's the acceleration of the whole thing, right? I'm not solving for acceleration of the individual ones, not yet. I'm just solving for acceleration of the whole system. And so basically, there's like a net force that pushes everything, right? This it's just some net force. We just say F net equals MA. Like for the whole system, MABC is all in here. And then it moves to this acceleration, all at some force to the right. It's a very general statement. But then they want to solve for acceleration. So you just do that, right? If they say for the whole system, you should be thinking of this, just the whole system moving to the right at some force that's equivalent to MA. So yeah, you will get F over all the masses. Okay. And that's how you answer, that's part B. And now C is the net force on each block. Again, we don't even have numbers yet, so it's all in variables. Net force on each block. Yeah, we have to do this. What is the net force? Wait. Yeah. All right. When you see this net force, let's see, net force in each block. When you see that word, you should be thinking of this. Well, this was for the whole system. I can write the same equation, but just for block A. So I can say F nets, but for A equals MA, right? It's the same statement. I'm just saying, the A in general experiences a force that's equal to MA. That's what they want. And they want you to solve for like, what is this net force? The MA is given to you, like it's a known value. And then A is actually the same for all of them, right? The A is just this. They're all moving at that acceleration because they're all together. They all move together. So this A is the same as that. So I'll just do the same for the other two. And then lastly, this is your answer for, let's see. Right, just net forces on each block, so it wasn't too bad. Now these is okay, now we need to solve for what is the force of contact that each block exerts on its neighbor. Yeah, it's a little bit tricky. Okay. The force of contact, okay. So hopefully you can tell from the language that when it asks force of contact, they want, what is it? These forces, right? These are the forces of contact. There's FB on A, C on B, A on B. These are the contact forces, right? They're all only there because the blocks are touching. So they wanted to like solve for it. Real quick, someone says, where can we show F net in the diagram? You don't have to. If you know how we got these, this is fine. We don't have to show like the net force. We just have these free body diagrams. You don't have to represent that. But yeah, so part D, they do want to ask you like, what are these contact forces? So before you kind of start solving this, you have to understand, right? Equal and opposite, right? So when A pushes B, we call it FA on B. And then when B pushes back, we say it's FB on A. You should notice that these two are the same, right? A pushes into B, B pushes onto A. So those two are the same. And then what else is the same? B pushes into C, and then C pushes back on B. like these like that, the greens are the same and the blacks, their circles are the same. So we're almost done. So hang in there. We can solve. Let's just focus on the green ones first, right? Because I think, right, you can just say as a fact, FA on B equals FB on A. Like that's just a true statement. And so we need to figure out like what is FA on B, right? What is FA on B? Okay, so what is this? Yeah, force. Okay. That force. Yeah. All right. If I find one of these, I find the other ones, right? Like if I find out what this is, then I can say that's the same as that. So if I want to find out what exactly like this is, I just do like summing the forces again. So I say it's just force minus FB on A. I'm just focusing on block A, which is F minus that. And then we always set it equal to MA. But in this case, the MA usually stands for like net force, right? The MA. This is actually equal to that. And you already found this expression, right? So it's actually not too bad because if you just plug in that A, was it? Sorry, yeah. This is all like F net, the MA. You just plug this in place of MA, and you technically already know F, like that's a given value. You know, you can write an expression for this. I'm just gonna move to FB over A. I just move over, I'm just isolating that. So again, I just copy this thing because that's we already know. And then what is this? Plus F. What is oh yeah, just F. Yeah, that's it. I think the solutions they factored it out and did something, but this is the same thing. Yeah. Yeah, we won't even need to do part E. Yeah, we're very close. We'll do part D. We'll finish this up. Now you need to, those were the green ones. Now we do the other ones, right? F B on C equals F C on B. So yeah, those contact forces are the same. No, those are the same. If I can just solve one of these, yeah, then I can find the answer because there are 4 contact forces, but only 2 different values for it. It's solved the exact same way. You just focus on one of the blocks. You just say, what is it? You focus on the middle one. You just say FA. Yeah, here. Focus on the middle one. The positive side is FA on B. I take this one, I subtract that one. This is equal to F net of B, right? MBA. And that, of course, you already have that expression here. So it's the same thing. If I am trying to isolate, you know, FC on B, right? So I'll just move it over, do what I did before. If I move it over, it's FA on B and FA on B. This, what was that? Do you see? All right, it's a little bit mind games, but like FA on B was the same as FB on A, which is here. So basically, this plus the acceleration, like the F net here was your answer. So anyway, I isolate this. FA on B is the same as what we just solved for here. So I'll write that out real quick. Right, plus F. So that's F, what's it? That's FA on B. You know, that's just that. This is the equivalent to what we solved for before. And then you have to add, what is it? You have to add, sorry, subtract, because I moved this over, subtract MBA, which is that thing there. Yeah. MA is messy. There you go. And part E is just plugging stuff in, but that's not important. You can do that if you want, but it's not important. It was pretty messy, but the main takeaway from this problem is the contact forces. Like if you are required to, you should be able to say FB on A and like the FC on Bs and all this. Like you should be able to point these out, right? All for the same reason. Just think about the wall pushing. If it's A pushing, a box A pushing a box B, think about if you're pushing on the wall, you're gonna give a force A on B, and then the box is gonna give you a force FB on A. Yeah, that was the main takeaway. The rest is just a little bit of algebra. And that's all I am going to do today. The recording for this will, I think I get a video file to upload it. I'll probably just edit the announcements in the canvas, because I'm a lowly LA. I don't know if I can just spam announcements. So I don't know if I want to send an announcement telling people there's a recording. Maybe I'll just individually message the canvas message again. Oh, I really hope this kind of helps. Hopefully, I really don't know, man. All right, you guys. Yeah. I'm glad I helped you guys. All right, you guys have a good night. I'll stay behind for some questions. Yeah, I will one day. That's the goal. Yeah, if anyone has just a random question, just say it out loud right now. We can talk about it.
For part D, would it also be minus as well for that on the left part of the equation?
I say I guess a part D, would it be
Would be the minus the fraction?
oh, would it be minus the fraction? Oh, part D. Sorry, is it like the red stuff here?
No, sorry, on the black part on the bottom.
Yeah. So yeah, it's okay. Yeah, go through it again. I'll go through it again. Okay, yeah, force. Yeah, minus FB on A equals MA. Yeah, so if I am solving for this. Yeah, did I forget that? Yeah. What's the question?
Wouldn't that fraction be a negative?
Oh, this thing? This thing?
Yeah.
Oh, would it be negative? Let's see. Would it be negative? Okay, well, you should have said this way is positive, honestly. So that way is positive. The net force on A was to the right, right? Because right? So it would be positive.
But don't you subtract the mass of A of acceleration to the left of the equation?
Okay, so what I did here, I added this. So I moved that to the right side.
Yeah.
So and then I subtracted the MAA. Oh, this thing. I subtracted that.
Yeah,
Oh,
wouldn't
yes.
that be negative
Oh.
as well?
So it's like, oh, it should be F minus this, right?
Yeah.
Yeah. Okay, yeah. Yeah,
Okay.
that's what it should have been.
And then for the red one, it'd also be F minus that, right?
Did I mess that up too? Let's see.
No. I think you wrote on the bottom. I'm just making sure that F is a part of that.
Yeah, this is the same F and then minus that stuff. I think you get the idea.
Yeah, I'm just making sure. Thank you.
Yeah, if you get the idea, you get the idea. Okay. Anyone else before we head off? A hawk question. I can take a look. Which one in your textbook? Oh, I was like, is there a hawk in? I mean, there's totally hawks in some of the questions. I was like, is there a hawk question? Like, maybe 4.36. I'll take a look. Which one then? Han. Oh, 4.34. Let's see. Oh no, not the bucket ones. No. We'll, all right, we'll give it a shot. So I'm going to do 33. Okay. These are the both 3.2. If the buckets are rest, what's the tension in each cord? Okay. Okay, so just real quick for part A is if the buckets are rest, what is the tension in each cord? Okay, so here we know, okay, tension has to be upwards. We can call that this. And then for the bottom, we know it should be, force of gravity, weight, so mg. So we know for the bottom one, it should just be T equals mg. Okay, so tension here is just 3.2, 9.8. All right, and then what about this top one? Hold up, wait, elevation. Yes, the top one should be the same. It's just, yeah, if you just focus on this system alone, oh yeah, then it's also pulling it down. Oh, I see. Okay. Up here. Tension here. Oh, I need to check something. Tension 1 equals, oh, okay, yeah. Yeah, just following the same logic. Yeah, okay. Yep, this one is also mg. And then sum the forces. I kind of skip that. What if we sum the forces? These should be different. T1, T2. Yeah, just follow the logic that we always do. T1 minus, is it T2 minus mg? It's not accelerating. Solve for T1. Yeah. Okay. So we have part A we got under control. This one is just mg. And then for top one, so even if I wasn't sure, I'm just like kind of going with the flow. I know that the tension is pulling it up, but I also know that it's not just the weight, that this also has to carry this other weight. And so that's the T2. And T2, you have it right here, right? What this tension is just going to be equal to that guy's weight, right? Because it's just pulling it up. So yeah, T1 equals the mass, the weight of this, so 3.2 kg, 9.8. Then we're going to add T2, which is the same thing. It's just that times 2. It should be like 62. Well, I'll do it. Yeah, like 62.72. Yeah, that's part A. Was 31.6 newtons. This is part A. And then part B. If they're pulled upward with that acceleration by the upper cord, what's the new tension? Okay, what's this? Okay. Okay, all right. Let me try something real quick. Two times. Okay, let's try this because when it's at rest, the whole system is not accelerating, right? It's not accelerating, so that's why when we sum the forces, like usual, T1 minus T2 and V equals 0. We set equal to 0, but now that it is accelerating, we can't do that anymore. So I'm gonna do the same, but I'm not gonna cancel out to 0. So again, just focusing on that first part here. Yeah, let's just see what happens. So yeah, now I need T1. Let's see. So mass, the mass 3.2. Oh, it's lower bucket. Okay. All right. Yeah, we'll try this. T1. See what this is. About what is this 66.72. That's is that right? Yeah, that's 3.2. Okay, yeah. 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 Okay. If you see what I did here, yeah, I'm gonna do the same for the second part. Yeah. Well, yeah, now, yeah, do the sum the forces for the bottom one. This is T minus mg equals ma. And so tension times 1.25 plus 3.28. What is that? About 35. 36 newtons. So yeah, it got bigger. It got bigger as expected because it is accelerating upwards. Yeah. And I think we did that. Now we can go into the other parts. 34. The cords accelerating the buckets each have a weight of 2 newtons. Determine the tension of the cords. Oh, is that part of the homework? 34? Hold on. Shouldn't be part of the homework. One. It's a bit of a cop out, but I'm gonna tell you not to worry about this one. Yeah. Yeah. We don't usually give you chords with the weights. I think yeah, 33 like that. This was something you get, but you definitely wouldn't get the 2 newtons in the chord. I'll tell you that. So yeah, it's I don't want to spend too long sitting here and just trying to figure it out. And I think I do need to go. But yeah, I think if you understand this first setup like that, that's the more important part. Don't worry about the other part. Yeah. Okay. Anyone else have like, quick question? Yeah, what's up, Jisoo?
Hi, just a quick question. Whenever
Uh-huh.
we're finding an angle, an unknown angle, do we always take an inverse tangent of y over x? Because I realized that during lecture, professor did x over y for some angles, so I was kind of confused by that.
Yeah, that's it's usually tangent, right? Let's see what circumstance. Yeah. Okay. So usually a thing where you see that it's in vectors, right? Yeah, a vector, just as from the first problem, if the vector was -6 and then +8, and now I need to find the angle. All right, so I'm thinking about it on an XY plane. Then -6 + 8, so it's somewhere here. This is -6, this is 8, right? This is the X side, that's the Y side, the Y component. If we need an angle, we would do tangent is Y over X, right? I think you know this. And so while I'm not gonna tell you like it's always like this. I mean, for vectors, usually because vectors you always have X and Y components. That's why it's like tangent. So I mean, if what the professor did kind of like messed you up, I would say try not to think about that. Just think about it like this. Always just ask yourself like what components you have. Opposite, adjacent. I think that's the best thing I can say for you is just make sure if you draw it out, I think you'll know what to do.
Okay, thank you.
Yeah, sorry if that's not thorough enough, but yeah.
Thank you so much.
Okay. Yes, anyone else? Any Han or Tim? Okay. I think I'll just end it here. All right. Good luck, man. Both of you. Of course. Wish you the best. Have a good night.